Hello and welcome to today's hands-on walkthrough on how to bridge the gap from SIL to HIL testing for battery management systems. My name is René Duty and I'm Field Application Engineer at dSPACE. Today I'm going to present you a demo which showcases the test case transition from software-in-the-loop simulation to hardware-in-the-loop simulation. The application of the demo is to test the battery management system control unit. This particular example is a low-voltage scooter vehicle. For this purpose we have prepared two setups. A standard Windows user PC running the SIL simulation and a small rack setup to run the HIL simulation with real hardware. Alright, let's go to the demo system. On the HIL side, there's our small HIL rack setup which provides the required physical signals to a real physical BMS ECU. Here in the safety cabinet you can see the black box. This is the real BMS hardware ECU. The small box indicates an error on the ECU side. It is an integrated version, which means that master and monitoring units are fully integrated into one housing. The simulator provides 16 cell voltages like a real battery and interfaces the ECU also via CAN bus. For this, there are very precise and galvanically isolated power supplies used. In this case, our high-end board provides up to 0.3 mV accuracy and 2 channels each. In addition, the ECU is provided with a current sensor signal and a temperature sensor, information via another board. In the lower part of the HIL, there is the brain of the system, the dSPACE real-time platform Scalexio. The cell emulation cards in the upper part are hooked up via high-speed fiber optics IOC net connection. On the real-time PC, there runs our MATLAB Simulink-based battery simulation model called ASM Battery. The model is an equivalent RC circuit model simulating the battery cell voltages and temperature behavior. The model allows us to test various features: SOC calculation, thermal runaway, and furthermore. The system is connected to a user PC via Ethernet cable. On a SIL side, we only need a standard user PC with dSPACE simulation platform VEOS installed. With VEOS, the two main software components are connected together. The same battery model as used in the HIL and the Level 3 virtual ECU are connected together. The virtual ECU has been generated with dSPACE generation tool SystemDesk. Level 3 means that we have not only used application software, but also basic software components within the controller. The BMS ECU consists of one master BMS and multiple monitoring devices which are communicating via virtually isolated SPI communication. For this, SystemDesk provides a SPI module for communication as an MCAL module. This allows us to test the ECU firmware on a level which is close to production code. For more information how to generate a virtual ECU, please check out our other videos or get in touch with us directly. Okay, let's now move to the actual demo. Now you can see a window showing our instrumentation software control list. The layout shows the pre-charge circuit and battery voltage and current. In this demo, we want to provoke the ECU to raise an error flag when the total battery voltage falls under the minimum allowed and configured voltage of 53 volts. To approach this border, we will simply draw a continuous current out of the battery. Once the border is reached, the BMS is supposed to stop the current flow by opening the main contactors. I will draw out 50 amps continuous current out of the battery, which is also signalized here. And interesting is the total voltage here. You may can hear also a beeping sound coming from the real ECU. This is a warning indication that we are approaching the barrier of 53 volts. Now we are very close, and with going below 53 volts, a voltage error fault was raised, and as you have seen, the lower and upper main relay has been opened. The ECU acted in the way it was expected. Now we will do it in a more convenient way using AutomationDesk to automate the test case, because doing regression tests we don't want to do the tests in a manual way. You can see here the AutomationDesk environment, seeing a test case here in the middle, which is a block-based way of implementing test cases. Each and every block is doing a different step. We have the initialization phase, we have actions and evaluations, and we have a cleanup phase. Most interesting is the action evaluation phase. In this setup, we designed it in such a way that we can decide which environment we want to select. We will start with the software-in-the-loop environment. VECU stands for virtual ECU here. I select this, and then I do execute the test case. I will also generate a report. Okay, I see that something is happening already in the output window, and when I jump over to control desk, I can see that the SIL layout is now activated, and soon I will draw again 50 amps out of the battery and wait until the virtual ECU in this case is giving a voltage error fault. Okay, as you can see, 50 amps are now automatically drawn out of the battery, and we are again approaching the barrier. This time without a beeping sound, because we are working with a virtual ECU. And as you have seen, again the voltage fault was raised, the upper and lower main relay were opened, and the load was decoupled from the battery as expected. Jumping back to AutomationDesk, you can see that the test case has been passed. I have here some information about the steps of the test case itself, and also a report was generated. Okay, since the SIL test was successful, I will now select in the environment the HIL, the hardware in the loop setup. I'll execute the test case. This is indicated here again in the output window, and if I jump over to control desk, I will see again that 50 amps are drawn out of the battery as expected. Yeah, not surprisingly, again the ECU gives a warning indication, as I did in the very first manual run. And once we approach the 53 volts, the voltage fault will be raised again. Okay, this happened as expected. Again, the upper and main relay were opened, and the test case was successful. Also, AutomationDesk is indicating this here and is generating another report, as you can see here. Opening a report, you can see what has happened and what were the steps performed during the test case. Here a description of the different test cases is given, but more interesting are the graphs that are drawn. One is the state of charge, which is starting by 7% and going down. Also the overall pack battery voltage is having a drop here in the beginning because the load is connected, and then it's further going down. And most interesting is the undervoltage flag, which is raised by the ECU, which is drawn by a certain level at 53 volts. Last but not least, I want to mention that there are further test cases that can be executed. We have derived from a EU everlasting project further test cases for cell undervoltage, overvoltage, balancing tests, as you can see here, pre-charge circuit tests and furthermore, which can be used. Yeah, and with this, I want to thank you for joining today's hands-on walkthrough on transitioning from SIL to HIL testing. We demonstrated how both virtual and real ECUs respond to an undervoltage test case using dSPACE tools like VEOS, Scalexio and AutomationDesk. If you're interested in applying this setup to your own BMS testing environment, feel free to reach out. We would be happy to support you.
dSPACE, your partner in simulation and validation.